So we have these meetings every 2 weeks, sometimes or maybe once a month, which discuss the hardware offload, which is not part of the TC patches. The P4 TC patches is a separate. When the drivers are ready, then these patches will be posted. All we're discussing is different intricacies. There's several vendors involved that may have slightly different approach to doing things. In general, this is just using the TC NDO with some small changes. So far, there's some drivers out there, not public yet, but they all use TC NDO. Some changes. Okay. People who don't attend this meeting have never seen this material, so that's why I'm going to present it. I'm going to present summary of this, and I will do a live edit of the document based on the feedback. Sorry, can you hear me? Oh, you guys are looking at the Wi-Fi. I'm sorry, it's so long, but they promised to fix. All right, I'll get started. So this is a document that is not public yet. It's only available to the people who attend the meeting. It's on Git. If you are very interested, send me your GitHub ID and I'll add you to the. And all it does is it's like I'm almost going to be reading of this because most of you guys have never attended this session. It captures the bi-weekly meetings, discussions. And this one is updated as far as June 10. Yeah, that was the last time this document was updated. And maybe one or two things are missing from the subsequent meetings after that. Okay, so we start with a view that we're going to adhere to the TC model. What does the TC model mean? Typically, what it means is this diagram may be one way to illustrate it is you have a hardware data path that is then reflected fully or in part in the software. So you could have something that's entirely in hardware, have something that's entirely in software, and you basically just, and you could have them working together with each other. You could have some pieces because the hardware may not be able to process everything. You could split your data path pipeline into two pieces. Okay? So that's the general idea in TC is you have anything that you want to offload, you would also want to represent it in software. It may not be performant in software, but you need to be able to represent it in software. The algorithms in software do not have to be the same as hardware. They'll be nice if they're the same, but they don't have to be. So those are general rules that have been around for many years. In fact, when we produce the patches we've been posting on the list are just for the software part. They have nothing to do with the hardware. This meeting is going to be discussing this part here, right? This part. Not going to be discussing the software data part. Okay. I guess no questions. I can move on. Another perspective for that the TC model provides is you can actually write your code entirely in software, test it, and if the hardware is implemented as per spec, then you can run the same data path entirely in hardware. Or as I said, I'm going to show a few examples of how the pipelines normally today get split. Right? And then what you have from a control plane perspective is a CRUD API that is used in Netlink. So CRUD stands for create, read, update, delete. So there's about 5 verbs in total that are used to control any of the P4 objects. There's several P4 objects. I'm not trying to prejudge what P4 objects look like, but from a very high level, one of them that many people will be familiar with is a table. It's a match action paradigm. You match something, you do something. You maybe move to the next table. You go back to the previous table. So there's a DAG which shows tables being connected. And there's a parser in the beginning. So you parse your headers. If you're trying to process headers, it could be entirely you're processing metadata, not even header. Metadata meaning, as an example of metadata you may be familiar with is the TC SKB mark, the SKB mark or TC index. Things of that sort that are PNTC. Those can also be used as classification input. The table, the control plane is capable of updating. When you're only running software data path, it's only updating the semantics exist in TC already. You say skip hardware, then it updates only semantics for software data path. You say skip software, then it updates the hardware. And there's mechanisms where you can say, try to offload first, and if you fail, as a best effort, put it in software. Although, in the case of P4, unlike, say, TC Flower, you are already aware of the resource constraint. When you write your P4 program, you will be able to specify that this table can only take 1 million exact matches or 16 million LPM entries or 5 ternary matches. You really don't have to. The best effort thing doesn't add much value because the software already knows what capacity is still available. So when you say skip software, and there's no space, you may get a rejection right away. It doesn't go all the way to the driver. Assumptions, again, what TC model means. Yeah. I think let's do it interactively. The problem is your question may be answered in a couple of paragraphs later. But go ahead. What's the question? No. Is it related to this or what I just said? Yeah. Sorry, use the mic.
Where in this picture is the P4 compiler?
I did not show the P4 compiler here because the purpose of this was someone is already aware. But let me see if I can give you a diagram.
Well, no,
I'll show where the P4 compiler would play. Here. So if anybody remote as well, please let me know if anybody pops up there. Yeah, okay, that's the one. This is just showing this is a really bad one. Hold on, find it. Oh, that. I'll just verbally respond. Okay, so you write your P4 program, you run the compiler. There's two, depending on your command line, you specify your backend. Okay, I just want it for software, in which case it will generate only eBPF code. You could say I want it for Intel's NIC to generate blobs that will work with Intel NIC. And then you can either load software only or hardware only. If it's the same P4 program, the semantics of the P4 program in software and hardware will be the same.
Okay, can you go back to the picture you had up before?
This is a runtime.
On this one.
It's showing runtime, yeah?
So
there's several things.
Somebody has a P4 program, they compile it.
Mm-hmm.
They compile it to P4TC.
They compile it for a back end. So the vendor back end will be this part here.
Okay, so
everything in green is generated.
I guess what I'm getting at is, so P4TC runs in the kernel. This is showing offload. How does the offloaded image get created? Okay, this is about offload. This meeting is about offload. I'm not going to be talking about how software works, but what you can see in this diagram is everything in green is generated. The TC and XDP are generated by the software backend. This one is generated by, depending on who the vendor is, it will be generated by the vendor backend.
The source is the same program. It's a P4 program.
Okay, but that's the back end. So the back end is created by the compiler. Is that correct?
The back end is created by whoever creates the back end. There's like 15 different backends.
Okay, so when I compile the P4 program, I'm compiling directly into the back end, and then I'm loading that through the kernel. Is that true?
Yes.
Okay.
So you're generating the eBPF code, right? Which then gets compiled, and then you load it using the regular mechanics for loading BPF program. But what we're interested in today is talking is this passage, not necessarily this. Although I'll show bits and pieces of this. If it's interesting to show some pieces of this, I will. I have some examples for it here. I guess the audience may not be very aware of. So what should I pick? I want to pick something very simple. Okay, let's say something. This is a public example. You wanted to see some public examples? They've been available for some time. So here's a simple L3 program. Start with a simple program like this. Is this of interest to people here? I could spend more time. And if people are interested in seeing this kind of stuff. Okay. So here's a P4 program. Okay. Start at the bottom. But here is you have two. This one has one table. Okay. Very simple example. It's not intended to make you a guru. You have a table called the next hop table, NH table. You look it up using the destination header, which is going to be up by the parser, which is an exact match. So this is not an LPM table. This table is just going to be doing exact matches. It has a type. So whatever you see here, we call this annotation. Anything that starts with @ is an annotation. You can add annotations. You just have to teach the compiler what it means. So the annotation for IPv4 is to tell the compiler that some human would want to enter this as an IPv4 address at runtime, right? And that this is going to be known as dest adder. Where this is the compiler generates next is, if I go into the generated piece, what you're seeing here is what the compiler generates. I have a feeling this is slightly dated, but should be fine. Oh, it's from January this year. So it generates, for example, a JSON file. See the JSON file there? The JSON will say, I have a table which is running on ingress. It has a next hop. It's called next hop table. It has it can take a maximum of 2048. Remember how I said you are aware of your resources? It has, I don't know why now mask is generated, but it has a key size of 32 bits, which is essentially your address here. And the key field is there's one called dest adder, which happens to be the name we told the compiler to generate. Okay. And the actions it can execute there's one called send. Action name is called send to next hop, basically, which takes the port. If I go to the action called next hop, the type port. This is a Linux Netdev. So it could be whatever a dummy device or whatever name you want to give it. And this is the other thing. The other thing is it's a MAC address is another parameter, which is here, which is we give it a name of MAC address. It's a type. We've customized this for Linux, but not by changing the programming language, but rather by adding annotations that the compiler is knowledgeable of. Okay. And so this is what is used then by, when I say the JSON file is what this is. Okay. When we write, we have very simple API for the control plane. You have, like I said, CRAD. You can create, you can read, you can update, you can delete. When you start your application, you suck in the JSON file into your C code, write it in C or Rust. And then it's hiding you don't need to know a netlink bit, but it starts talking to the kernel using netlink. When it talks to the kernel, That's where you specify whether you want to go to software only, or hardware only, or both. The eBPF code, I'm sorry, is that enough for this? Because this wasn't exactly where I wanted to go, but I don't mind looking at it. I mean, I don't mind describing this if this is what people want to talk about, as long as I get an opportunity later on to talk about how the hardware offload is done. If you look at the generated eBPF code, we generate one for the parser, for you, Tom, and we generate one for the rest of the code. Okay? So you really do not want to look at this, but I'm sure the indentation is not correct either. But there you go. Now this one is trivial enough, but typically in some cases we would invoke kfunc for software only. So this code may invoke a kfunc here, or this code may invoke a kfunc to access these objects. These are not just tables. You have things which are called extents, actions. There's a bunch of object types that are not natural, let's say, to eBPF that reside over here. But the execution mechanics in software is done through eBPF. Okay? I don't know, what else do you want to see?
Another question?
Yeah, sure.
Can you go back to the JSON?
JSON. JSON, if you're familiar with P4, it's very similar to what they call P4 info if you're using a. Go ahead.
So does this JSON completely describe the program?
No, it's control. For example, the parser is not involved at all in this.
Okay, if you take out the parser.
Yeah.
So I guess what I'm getting at, what's the JSON used? What does it do? How do you use it?
So the JSON is used. Maybe I'll show an example of program, of a usage with this.
I can help answer, Jamal.
Yeah, sure.
Yeah, so JSON is actually helping with the mapping of a P4, which are logical objects, and giving some information on to the driver, because driver is constant and you have different programs. So driver needs to know what those things get mapped to in the device. So that's one of the description that JSON does.
Yeah, actually, that's a very good point. Thanks, Anne. If you notice, every object has an ID. Right? Every object has an ID. And the IDs could be hierarchical. This is one way to overcome the Flower hard-coding semantics, where every object in Flower is hard-coded. As long as it can synchronize the IDs between hardware and software, and you never ever have to change the kernel, period.
Right. But I'm still wondering, and we talked about this offline, whether or not the JSON could actually be an IR. And then if you combine that with a common parser representation, would it be possible to put all of this into one IR that we can then allow any arbitrary front end, any arbitrary back end? So I'm still interested. Maybe we can take it offline.
Yeah, we can talk about that.
I would love to see things go that way.
We started with what P4 does today. That's what people would do. They do not describe the parser in their info. But so for the people who know what Flower does, when you write Flower code in the kernel, if you have to make any changes, if you have to add a new parsable field, you'll have to go and change or dissector code in the kernel. You'll have to change Flower code to be aware of this header. You'll have to go and change IP route 2, and then you will have to change your driver probably, right? And the way we did this is there is nothing to change in the JSON file describes the IDs. If you're to load your driver here with the same IDs that the hardware is aware of, then the driver doesn't have to change. You can arbitrarily write a brand new program today using P4 that's proprietary to you. And I'm not saying that's the right thing to do, but there are people who just want something different, right? Without changing any kernel code or user space code. The process of just you changing something that goes out to the mailing list, that will consume months with this is essentially, even if you ignore just the eBPF code, if you just want to do hardware offload, I don't want to claim it's instantaneous, but some people have said it took them a few minutes to get it. In any case, back to the agenda, I just want to say that this meeting, this discussion, which I hope we have enough time, is to describe to the rest of the population, I guess, what we have been discussing in those bi-weekly meetings. And hopefully we can get some feedback, and then we can make this as a release as part of the conference documentation. We'll release this document as well. Okay, so back to what the TC model means. TC model means you have this kind of architecture. You have this kind of semantic where I write something in the control plane and I could say I want it in hardware or software. There are other assumptions that we're making. This is just feedback on the mailing list. I'm not saying that. So there are vendors who could load multiple P4 programs, actually generate several programs, and have your hardware run more than one program, depending on the parser, or depending on what things called profiles. You have different tenants running different programs on the same hardware. But as a starting point, we're not going to go there. What we're saying is the program will be loaded at probe time. So when your driver probes, that's when we load the program. Right? That means you can only have one P4 program. And we're not going to stop some vendor from running multiple programs, but we're not going to allow it. But initially, we're only going to say there's only one program that can be loaded, and it only gets loaded at probe time. If you want to change your program, which you're allowed to do, then you go build your P4 program, load it, then do a reset of your driver. So there is no high availability, but high availability friendly. So there are vendors, there are vendors who can load multiple P4 programs on the device. We do not, we're not going to go that path initially. That the software P4 program and binding is done through the loading. When you, based on what the compiler generates, you can say, this program is also going to have a peer that does offloads. And I'll show some of that semantic. Now, the vendor will ship the default P4 program that goes onto the NIC. Now, that program, you should be able, as a user, to compile it yourself and test it. Make changes to it and test it. I don't know if they'll support it if you start making changes, but it's available for you to do. If they want to support a software part, then they will also ship you probably the generated BPF program, or you can generate them yourself. So there's total freedom. That's the agreement amongst all the vendors that are attending this meeting. They agree that that's the way it's going. Okay. So we've been discussing things. How do you replace this program? I think at one point the idea was you put it somewhere and then you provide a SIM link to the new program and then to make changes. But I think Sridhar was saying in one of those meetings that this will require changes to DevLink. We're trying to avoid changes as much as we can. So at the moment, the P4 program is supposed to be per NIC. If you have two NICs from the same vendor, on the same board, and they may load totally different programs. That's the idea. I think today the concept is if you're going to have the same NIC, like E8110 from Intel, then it's going to probe for the same program. Whatever firmware it loads will be exactly the same. And we're saying that, look, we may allow for you to have two programs for the same version of the NIC on the same server. Any questions on that? Yeah. Mike, please, Mike.
You spoke that you'd have one P4 program by default, right? Some vendors might support more than one, but if you have one, you need serialize so you can do a rewrite and then do a redirect.
You want to run the first one, then the second one.
Yeah.
I think vendors, as far as I know, all the vendors will support that. But we just want to get the initial patches in. And we're saying that we'll only allow one as a starting point. that does not preclude you from doing what you just said. But the public support of what goes in the kernel initially would only allow for one.
Okay, thank you.
Right.
My question is how you work with the hot reloading of P4 programs. So when you need to update them in runtime to jump to a new code, or what happens to the NIC? So does it drop the traffic, or is it smoothly moves to a new version of the actually the software?
At the moment, it's total. There's no availability basically. It's almost like your IP link set down and up. Then the probe will go and read the new code. Right. So if you change it, you'll have to bring down the device. For now, I know for sure that I've seen vendors where you don't need to do this, but we are trying to conform to, we're starting slow, right? That will allow for that, unless you guys think differently. What do you think, Alex? Yeah. Well, most people don't need to do a live update. Well, okay, you probably do.
Probably, but in my case, it's like every time. So we're updating the programs like daily, several times a day, and so it's really important to update the code every time. So,
okay, all right. So you do have that need. Your NIC can support this. I know that it can. We're just going to stay out of it for now, but I understand what you're saying. Because we want to have there's at least one vendor that may have had issues. That's why we only have a common denominator for everybody. Okay, so the conforming models that we support, and I'm going to list which ones are already supported. Okay. So number one, this is the traditional, this is a simple case, is you just have a software data path. Those are, if you look at the patches we've been pushing, these are what they're doing. And I'm giving a very simple example. You write a P4 program that looks like this. And then when you generate the code, it looks exactly like, right? So that's the trivial model. In Flower, the example of this would be, you basically don't have any offload. Fortunately, if you have a NIC that has offload in Flower, it will work. You know, in case of TC, if the NIC doesn't, we don't need to load in all this extra code. That is needed for hardware when you don't support hardware offload. And likewise, if you don't want to have any software, there's no need to have extra code paths that exist just for the sake of software. There's no distinction like this in Flower or any of the other TC offload. So the first model is I write my P4 program as trivial as the one I showed here. And when I offload, and then I can say, I only want it to run in software, right? And the second model is I only want it to run in hardware. And when you load your filters, you just say, I'm only interested in hardware offload. I don't want this extra garbage or baggage. I'm sorry, the baggage. I don't want to load any eBPF programs because I'm not running anything in software. The third model is a hybrid. So I should say the first two models, very well supported by TC today. Even if you do Flower, you can do this with the caveat that Flower will still, if you have a NIC that does offload, it will still try to offload for you. There's a hybrid model where you write your P4 program, and then you specify for various reasons that I want. For example, like I showed when I showed this code here, it showed that the P4 program had only the exact table had only 2048 entries maximum, right? L table 3 size was 2048. The JSON, generated JSON will show it better, right? The table total entries is 2048, and you want to do 1 million entries. So you may decide to use this model. This is nothing new. This works in TC today. You may want to say, for this one table, I want 2048 in hardware, but the rest in software. right? So when the packet comes in, if there's a miss in this table and the packet goes to the exception path, which happens. The software in this case helps hardware. Same thing with this other table, right? If you have a miss, you go to the software and then, but it skips this table, it goes to that table. This is nothing new. This works today. If you have Mellanox and you're doing Flower, you can get this work. Okay? Then there's a pipeline continuation. So there's another model, and I'm just trying to list a permutation of these possibilities here, because we have discussed this in the meeting. In this case, you'll basically have a table that requires you to run two actions because that's what your program says, that this table has action A and B, but your hardware doesn't support action B. In that case, the exception, whenever there's a hit on your table, but you have to execute action B, you end up going to software. And the software has this continuation table. And if you're familiar with Flower, when we say continuation in software, that's what it means. But the hardware will, in this case, I don't know if anybody is here from media that qualify this for me, but you have the table entries cookie is used to look up this continuation table in order to execute that action, right? And likewise, if it's a hit action with A, then you go to the software table. These are two different code paths. In this case, the continuation table is not part of the P4 program. It's part of what gets manifested in the. So this works today. There's nothing new here. This is how Flower works. I can have a table that has an action that doesn't get supported in the hardware, and in that case, I'll have an exception path that takes me to software. The last one, which became prominent in this meetings, is this one, which is still a continuation, but imagine you have a table, a whole table, which let's say it's doing exact matches, and the hardware does not support exact matches. In that case, you want the continuation for that table to be in software. So this is not currently supported in TC, but it's something we will add when we do the hardware offload. Okay? Any questions on this model? It makes sense? Anything online? Tom? If you started the question? Okay. All right, I'll continue. The workflow. I don't have internet because I couldn't type. I'm sorry, but I would have clicked on that and it will show you a lot more details. The idea is you write your P4 program, like I said. You generate your different blobs, not blobs, but in one case, you generate this JSON file, which I just showed, or I should back to this. If I look at the generated stuff in here, see that there is a JSON file, which I showed. There's a couple of files for the parser, and there's a control block itself. Then you have this thing called simple L3 template. This is just an enumeration. It's a manifestation of your P4 program into the kernel. It's again using TC. You say my pipeline it's called simple L3 because that's what your program name is. Right? If you look at simple L3.P4, I'm going to create a simple L3. It has a pipeline ID of number 1, and it has only one table. And then you create your actions and you specify the parameters. Then you create your, then you make them active. In any case, I'm not here to discuss this deep. Just want to point out that there is a template phase, which is what this is now saying, that you will have these steps, right? You run the template, and the kernel becomes aware. What are your tables? What are the constraints? You then, we prefer to use TC blocks. We've been sending some patches here and there to fix up a few things in TC blocks. So you say, I'm now going to start adding ports, like Netdev ports, that will be used by this program, that will be subjected to this program, to this program. I haven't bound anything. I haven't said which program. I'm just saying I'm building a block of TC ports, using the TC block construct. Then you add a filter, and say, okay, that TC block number 21 is tied to my simple L3 program. And then, of course, after that, now this this becomes valid, right? You're now adding control entries. You're adding entries to the table, to the software, to the app. You can manipulate actions, extents, etc. Right? Anybody familiar with what P4 extents are? Essentially, they are closest I could think of is like the BPF helpers. If you're familiar with BPF, we can for that. If the language doesn't give you enough ammunition to specify something, right? And specify extents in P4, and we support them as well, right? And from if you're running a software, they get invoked through the K function. If you're just running a software data path. If you're not running a software data path, then the only thing of interest is the control plane to the hardware. Okay, and basically the last thing is after you've taught the kernel what you want to do, you start doing control plane. Okay, so what I just showed you was the pipeline. There is one semantic that is not in that template I showed you, is the concept of hardware offload. So when you load your program, you tell the kernel that this program is subject to offload, right? This is just the time sequence diagram, which essentially describes what this is. I will probably skip it because there's nothing exciting here. You just basically, you run a bunch of commands. Every time you run a TC command, it sends something to the kernel, to be a success or failure. And when you're done, you do this thing called, you seal the pipeline, almost like loading an eBPF program. Loaded it, it's sitting in the kernel now. Nobody may be using it, but it's there. And likewise, when you're removing the program, you'll send a delete pipeline. All this is using Netlink. And it is going to remove all the constructs that are needed, are in there. Okay. So, again, like I said earlier, everything has an ID. That's how you recognize it. The program has an ID, the tables have IDs, the actions have IDs, the parameters of the actions have IDs. This is how we avoid hard coding anything in the kernel. So the driver will know what these IDs mean because you've loaded, if you're doing offload, because you have loaded the hardware binary blob already. So if I send an object with ID 1111/123/4, it knows exactly what it is. It will, and I'm going to describe later on how to synchronize between what the software thinks the IDs are and what the hardware thinks. We still don't trust that someone can just send us an arbitrary construct and we'll say, oh yeah, it's got the right IDs. Let's just tell the hardware. We have a mechanism which will verify this. Okay, so step one. So I listed the 4 steps. First one is the provisioning of the P4 program, which is what I'm showing here. The second one is creating the TC blocks. I think if you ever use TC with blocks, you should be very familiar with this. We have made some changes. We're making some small changes. So this is important. When you add standard TC, when you add ports today to a TC block, at the moment, when you invoke the TC NDO, you have to invoke it for every port. Okay? In our case, it will be invoked. So every time you invoke the TC block to say, I want it 0 to be part of this block, the driver will come back and the callback. So you have one callback. Invoke for each one, you get a callback, and now you have another callback for each one. In our case, if it's the same vendor, that's one of the assumptions. And when you invoke, are they coming in or? Welcome. So when you invoke the driver, I should go here that our approach differs a little bit from TCNDO, right? While the top layer, whenever you add a new Netdev to the list, will invoke the hardware. The only thing the hardware would do is not to give you a callback, but to add a reference count. As an example, if you look here, we added ENO1 to block 21. So this block have IDs, right? And this will invoke the driver. The driver will recognize that there is a callback I have to register, and it's going to invoke the registration, the TC infra. Say, okay, register this callback in your list. Whenever you try to talk to block 21, you invoke that callback. And it increments a ref count. The next time we add ENO2 to the same block 21, this will be invoked. The only thing is the driver at this point will only increment a ref count. It knows there's 2 users, but it's not going to invoke the registration callback. That's one change that's different than the current TCNDO. Current TCNDO, when there's eventually, if you add a rule that has to be offloaded, it will invoke each callback. So if you have 20 Netdevs, it's going to invoke each Netdev independently. Like a broadcast domain, in our case, it's a unicast to the driver. So per driver, there will be only one callback. You may have multiple NICs. And if they have different drivers, then they will only invoke us. Right? So difference number 1 from TCNDO. Like I said, we try our best to keep the NDO as is. This is one change. And if it comes to it, then we may end up poking the NDO and calling it something else. But at this point, this seems to be easy to do. Right? At least from the current prototypes of the drivers, this works fine. Likewise, when you try to delete a device like ENO1, you're trying to remove it from block 21, then the NDO is invoked into the driver just decrements a ref count. And the only time it's going to invoke you to delete your callback is if the ref count hits 0, right? The last Netdev has been removed, then we call the unregistered callback. Current TC model is very simple. Every time you delete, you will be invoked with your callback. Your callback is being invoked. Okay, go ahead and clean up. There is no cleanup, only done once. The beginning, in the case of registration, and at the end in case of the deletion. Any questions from people who write drivers? Like, yeah, Mike, I know he doesn't need a mic, but people remote me,
So one thing I'm wondering about here, so this is something that the drivers or the hardware is running your BPF program, correct?
No, there is no BPF in the hardware at all.
Or, well, whatever's the thing you generated before with the P4 to TC is running on the hardware, correct?
Yes.
So what kind of handshaking do you have in place to make sure that the program you're wanting on there when you're trying to put this all together is actually running on the hardware?
Yeah. That's Tom's favorite question. I have it like punch. We need to validate. So everything that goes from control plane to the data path everything that you send down better have the same IDs that this guy in green here expects them. Has the same semantics. It has to be verifiable.
Well, right. I'm just wondering what we have or what's set up in here to lock the two together.
We have something. Maybe I should have brought it up at this point, but it's further down. I'll discuss that. I'll ping you to see if it answers your question.
Okay, yeah, because I'm assuming there must be some sort of globally unique identifier.
If somebody wants to offload.
Offload. Oh. Yeah.
Obvious. Or general and possible.
The answer is yes, but with a but. Okay. I know one vendor at least that publicly says they can write GRO with P4. I don't know, is anybody here from? I don't know if Shannon can answer this, but AMD basically says they can do this, but it's not. It depends on your hardware. Can your hardware support that?
No. Take the hardware out of the equation.
Right.
Let's assume that finally we have programmable hardware. It can be P4. It could offload eBPF. I really don't care.
Okay.
We have something in hardware that can do whatever we want. It's Turing complete for protocol processing. Now my question is, assuming we have that, what's the best way for the kernel to interact with that hardware in order to achieve functionality that we want, like grow?
So, to say, as far as I know, that some people say, I haven't seen, it's not public. That's why we didn't want to put it in here, that they can upload grow, for example. However, our initial push here is just for match action table. Just because of the TC semantics, and there's a very big use case for just that, instead of worrying about, can I implement my own TSO, for example, using P4 or some programmable.
So I'll just give you
Your mic
an idea.
is on?
Oh.
Okay.
Yeah. So GRO ultimately, actually, Jamal translates to a match action table and something called registers in P4. So, per flow registers that maintain the state and you check the state. Something very similar to what we do for the connection tracking for sequence number window check and things like that. So it's a new flow comes in, you identify it as a new flow. The hardware should be able to add a new flow dynamically without software's help. And this is, again, if you do a full connection tracker offload, this is exactly what hardware does. It's called an auto add of a rule. So it's a path where it says, okay, does the flow exist? Doesn't exist? Add a new one. Add a new one, and then for every packet, keep incrementing the state. So you decide when your RSC context closes in the hardware. So it's a very, it fits a very good P4 model. So you have to describe it in your P4 program. What I can say, I believe AMD does have it. In our first generation, because we focused a lot more on getting the RSC performance implemented and get the best performance for TCP IP4 IPv6, we limited it to TCP. So it's not something which is more generic than that. But yes, there has been a lot of ask for that.
So thanks, Anjali. So as long as you can prescribe it in a match action table, it'll be doable. But I would like to add a comment there. We need to have access to the PCI, to the host-bound interfaces like PCI, right? Because that's going to become important for, as opposed to just packets coming in, match action out. You need to somehow consider going up to the host through a PCI block of some form.
Yeah, this is.
Oh, I mean, sorry, we should have. Is there a second mic? Maybe we can pass around. Okay.
So,
Angela, we're going to need a second mic.
Yeah. So, yes, you need to have the PCI interface because finally your packet is delivered to software. GRO is an opportunistic offload. So if the hardware was able to do it, great. And maybe hardware did it can coalesce up to 64K and you want coalesce all the way to 512K. So you can run it further in software as well. So you can, and that part is not at present. What Jamal is trying to say is that part is not what, he has intended to code on the software side, but, the regular GRO path will pick it up. So yeah, hardware coalesces some amount or not at all, and then software coalesces further. I think Eric might be here and Eric is not here, maybe in the other talk. He's using that with our GRO logic. So the reverse of big TCP. So he gets the help from hardware to coalesce to 64K, and then, it continues to coalesce to 512K.
Okay. Well, let me continue. I think, yeah, we're 1 hour in. So again, the steps are to provision your P4 program. You create your block of ports, create a filter. The filters are whether your program called myprog also has a hardware peer. And then you start adding entries and say, I want this entry to go in hardware and software, depending on what your hardware is capable. So So step one was basically, we basically had to make small mods to the TCNDO. You can't just, this is not a broadcast thing, right? You can't just, every time you want to add an entry, the way TC block works today, if you look at the NVIDIA NIC, is you have to send that rule to every port. So you're replicating all the rules. Basically. You're just sending one. Okay? That's one change. The other is our tables in P4 are shared. You just basically attach ports to them, say all these ports use the same table, as opposed to I have a port per Netdev. Right? The next part is how do you bind P4 program to a TC block? And this is how you do it. This last part is unnecessary if you're only doing hardware offload. You don't need what I just highlighted there, right? That is not needed, this part. All you're doing is hardware offload, then you just don't need eBPF at all. If you are doing hardware offload and you need a software exception path, then you absolutely need eBPF. And as I was showing earlier, so in the mailing list, there's a lot of confusion. People think, oh yeah, we're just trying to compete with eBPF or whatever. But exception path could be here. Extension or exception path. There's a big difference. It's an exception path if I don't have enough capacity in hardware. It's an extension path if I'm taking my pipeline and I'm extending it into software. Again, if you're, like I said, you don't need to load the PPF program, and this meeting is not about PPF programs, but the hardware offload part. Okay, so, actually, this is probably, the font is probably too tiny here, but if you know this piece here, this is where the BPF software, if you need software, this filter will load the software using this piece here. Once it's done, then the P4 software infrastructure will now start talking to the hardware and say, okay, remember when we attached block, we got a callback. So you say, all right, please create my program. The driver increments the ref count at that point. You know, now there's a user with a filter. You're done. And again, so if you don't remove the filter, you don't delete the TC block, you still have some reference counts in the driver. So to totally remove your program, you have to delete everything.
I see that when you added eBPF program to the TC, you like loading it to the kernel, like compile it. I think you should also considering add it as a eBPF ID because the program itself can be very, very complicated, and you may want to like have a very custom load of that eBPF program. So to catch up with all the data, probably when you update the program, you still want to preserve some maps to reusable or something like that. And when you load a program from the object file, you like lose that possibility. So you limit your interaction between P4 offload and eBPF. So with reusing the eBPF object files from the eBPF ID, so load it into the kernel differently. So from that, you can leverage a lot from eBPF when you like not having enough possibilities from the hardware to upload.
Yeah, so we either have a hybrid mode or entirely software.
Yeah. So it's for hybrid or entire software. Okay. So you should be able to push eBPF as like separately, not a part of that tool chain, probably.
So yeah, sure. I mean, what this is showing here is this is how today when I load, we're using TC to load the eBPF code. It makes a system call, but this could be entirely a separate tool. This is how TC works today. Yeah. The TC, when it uses the loader, it's kind of not very well, it doesn't get a lot of love, but this is how it started and it still works like that. But we could use a different tool. Maybe I'll talk to you after on your experiences. Are you going to speak about this part?
I think not this time,
Okay,
but we can handle this offline.
Or I'll send you email. Okay, so when I'm registering the filter like this, that's when that hash thing. So, and I'm going to describe it later. Okay, let me go through the add, delete, and then I can describe the connection, the synchronization between what the software thinks the IDs are and what the hardware. It's a scheme that seems to be robust, but we may have holes. Okay, so this is the runtime. Now, maybe better off I just show you an example of this program because I already showed you this program, right? I'll show you the JSON, then it will probably make. Okay, here's this program here. We're creating on this table. So tables have paths that look like Unix paths, and they're based on where they're being invoked from. So if you look at this P4 program, you will notice that the main control block, it's like main in C, is called ingress. You'll see my program name is called simple L3. So there's some meaning to this madness of this syntax. I'm looking at the table object. If it was an extern, it would be extern, which is referenced in a block called ingress, right, of like the function which invokes it. And the table is called next hop table. And I'm specifying the dest address as 10.0.092.132. If I do that, from the JSON file, I know how to parse on the command line. This is the command line tool. What does 10.99.0.0.1 mean? Is because you've told me it's IPv4. We have type parsers. So the type parser will parse that into a 32-bit big Indian semantic value. And I'm saying that the action that I'm going to use is called send next hop, which you're seeing right here. I remember we said TC type is dev. We're saying there's a keyword called param, which says I'm about to tell you what the parameter is. The parameter name is port at ID, and it's port 1. So this happens to be a Netdev. Okay? The next parameter is source MAC, which happens to have this MAC address. The third parameter is test MAC, which happens to have this parameter. And if I look down here, you will see that all these actions have ID and all the parameters have ID. So this action called the next hop resides on the ingress as ID 1. And one of its parameters called port has ID 1. And the second one called source MAC address has ID 2. That one called destination MAC address. And of course, these are the bit width, right? The type is mostly for human. The name and the type are really for humans because you can write a CLI or you can generate a CLI. And all right, so that's how we would. Suppose it would be crazy for you to try to enter 16 million entries using the command line, but we have API. If I have the API here, I can show it after. The API is very simple. You do a create. A create looks exactly like this on the API level. It takes something that looks like that. It takes a parameter. No, it doesn't need to see human readable format, but a big Indian IP address will take the ID of the action, which happens to be 1. So these are all TLVs in Netlink, right? So I can hierarchically build them. I don't need to do anything. This is why I'm having challenges with these eBPF people. In eBPF, I'll have to reinvent all this stuff. I'm getting it for free. Once it hits the kernel knows how to parse, how to validate, how to do security checks on this stuff. None of that code is written by me. It exists. And it's very important, right? For the mechanics of what we're doing here. So basically, this just describes how that thing will end up going to the driver. So the registered callback, which you saw earlier when I added the block, will be invoked. So it happens that this is eventually going to end up in the TCNDO. And that's where the magic of validation, etc. I'm going to skip this part a little bit. Let me jump to the description of the synchronization is the object ID mapping. So all objects are 32-bit in size. So the program has an ID, all the tables have IDs, all the parameters associated with everything have IDs, and there's a hierarchy, really. So there needs to be some synchronization. The front end of the compiler is responsible for generating the ID. So it doesn't matter whether your back end is. You have the same P4 program, whether you're generating for hardware, using your hardware backend or software, they'll get the same ID. Okay? So that's step number one. Step number two, once you load it into the hardware, the driver is aware of this ID. Knows my program has the following IDs for the following objects with the following parameter sizes, etc. Right? So I'm going to skip this part. So here's an example which I just showed of an action. This actually, it so happens it's the same action I just showed you. This action basically just does just sets the source MAC address, which you program through the control, and the destination MAC address. And this is how you tell the kernel what it is. And this is how the JSON looks like. I think I went over this. But let me go into the signature. Correlation of what is in software versus what's in hardware. Right? So what we did was, of course, we need to ensure the two twins, what's in hardware and what's in software. If we're using software data path, also use the same IDs. If it's coming from the control plane, it's using correct IDs. In that case, we iterate. We are familiar with the objects and their hierarchies, right? And so our pipeline, there's a hash that's generated. Okay? The hash will work all the objects and feed on their IDs. For context, let's say we have a pipeline ID I, which has n tables and m actions, each with j parameters. That's an example. Okay. The contribution for the pipeline ID, just the pipeline ID, will be hash of I. And we have a hash that we take like 2. I don't know if it's the best, but that's what we're using. A table ID has a table ID TI. Contribution of all the tables would be hash of T1 to Tn. An action ID has an ID I, an action has an ID I, and all these parameters have an ID ij. So action I will have an ID of Pij to the j changes. So the contribution of the hash is the following, right? If we had extends, it would be the same thing. Eventually, we end up with a hash, and this is the hash here is computed using the Blake 2. Right? When do you compute the hash is the other issue. That when is the right time to do it? So if you remember earlier on, I said that the template, or I should show you the example of a template here. Generate a template, which is for this simple example, because I've been using this as an example. At the very end, once every object has been manifested in the kernel, you say seal. You say it's ready to use. That point, this TC infrastructure computes the hash, right? And when right, so when to compute? When the pipeline is sealed. Once I say it's done, then we tell basically this TC infra, not the driver, the TC infra. The hash is blah. On the hardware side, one option is for the driver to compute it when we load the block. Right, so we don't want to keep doing this at runtime every single time. So because the information and all the IDs are the same, when you send your objects, these IDs will be annotated in the data structure. And the driver, regardless of the implementation, it should be able to compare these IDs as being the same. So for example, the driver could reject your entry because you sent something bogus. Now listen, what holes do you see in this? This has been implemented essentially on a prototype drive. Does that answer your question, Alex? But you asked Mike to Alex.
Yeah, I can see where you're trying to go with this. I'm just not
entirely. So in my mind, that's the thing is most of this should probably be something that's generated at compile time in terms of the hash versus runtime. I'm not sure why it sounds like you're computing the hash every time it gets loaded.
Yes, loading time. But do you trust the compiler?
Well, essentially, what would be looking. So, well, I'm thinking more from like in the case of UEFI, for instance, you have to end up signing everything with like UUIDs for like all the different bits and pieces. And the expectation is, okay, well, I signed off on this. So if you go looking for this function, it's going to be under this UUID. So that's why I'm just kind of trying to think in terms of this hash, what's the possibility for collision and such in terms of changes?
What we talked about was like a SHA-3 hash, which is like very, 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 very rare to collide. But yeah, I mean, we talked about both possibilities, and it was more of like let the driver do it instead of the compiler in terms of trust.
I don't know. There was the question of whether we trust the compiler or not. Where's the trust boundary? I mean, we trust the kernel. I mean, it's just validation is, I don't want to call it zero trust. If it trusts nothing, then you will have to validate it. Not at runtime. That's what we're trying to. So, and then of course, if it's doing it on every control plane message coming to the hardware, then it's a bad thing.
I might almost treat it like an internal module, something along those lines, where, okay, when you compile your product,
when you compile your outputs, you should have a header file that you can include with anything that's going to access this. They'll have your signature for it. And then anything that's built for your, like the driver or the BPF should have a signature in there saying, okay, yeah, here's my signature so I can verify that, yes, I meant to run with this header file. So that when you put everything together, we all can talk the same language. That's kind of what comes to mind with this. I'm not so much concerned about security as will it all actually work together? You know, as soon as somebody changes a header file somewhere, everything's going to blow up otherwise, kind of thing.
Yeah, I think, Alex, you're thinking about like a vendor signing their images when they compile. Yeah, binary signing. We are completely avoiding this because the P4 compiler will be handled by customers and everybody. So like in our case, Intel is not the one signing. They are writing their programs and
header file. This is what I'm looking for on the binaries that either off with.
yeah, but header file, like then I have to update the kernel again if I change a program.
You going to be able to go blend the user space type.
Yes, but I cannot. Did you say that I should put the key in the header file in the kernel? I mean, that won't work. Okay.
Also important with this for it. And then it's okay, I'm go ahead and register this, and it better give me back that, or I'll either give it, it'll verify, or when it registers, it gives me back the signature so that I can verify that yes, I'm working against the binary blob on the hardware that I'm expecting.
So this is actually the fundamental point. You want to have a true digital twin where if you have equivalent functionality, you need a way to measure it. Best way, take a hash of some common ancestral source code, which I think should be an IR. Take that hash, distribute that to all the binaries, and then you have something to compare against. I really don't see any other way to scale that problem. So you want digital twins, as you say, then we need this hash model. But I also think it should be, you know, quite generic. Any binary that's generated should be able to do this hash trick.
So the IDs is the source of truth that we use, assuming the IDs are exactly the same. Both sides know what these are. If I have a table foo, it has ID 5. Instead of looking at the source, when initially we started with saying, okay, the compiler knows the source, it can generate a hash for us. But the question is, a human could manipulate that. So we're looking at it more than just as a zero trust problem. Okay, I don't want to claim we're implementing zero trust, but we don't want to trust even the compiler or the kernel. It's computed when you load. That's when we'll verify you are who you are. Right. So the IDs are close to what you're saying, Tom. They're derived from the code by the compiler. The compiler gives internal IDs, or actually in this case, externally visible IDs to different pieces that are. Huh? Oh, okay. Can we put them on or? Oh, I have to unmute me? The speaker. Yeah, the virtual speaker. Okay. The virtual questioner. Okay, people use, there's only one mic unfortunately, Angela. Do you think we can get a second one? No, well, after this. It's too late now, but. There is no question. Is there a comment? Someone just clicked the question thing by mistake. Okay. All right. Sorry, you wanted to ask something about this? Okay, maybe take the mic, please, because people remotely are complaining they can't hear. Okay. Yeah, so these IDs are describing the objects that are in the program. It sounds like it's reasonable so far, but we will look at the UEFI one. I think you said UEFI approach to everything is, what is it, Alex? And that will give you less collisions. How long is this key? Is it 128 bits? Okay. Right? 128 bits. Okay. Okay, I'm just going to say long string. We'll find it. Okay. All right. I can go back now. Lyle. Sorry, Carl. Some people are speaker volume is very low for me. They can't hear me that well. Remote. Can you hear me now? Is it better? Maybe ask people remotely. Okay. Maybe I'll better to use that mic, or I can hold it. So okay, going back to where I left off that time. There are several models to deploy this. I don't know if how many people are familiar with DPUs, or what I should call XPUs. One way is, for me, we call it the smart NIC mode. Smart because it's good joke. Because it has an ASIC, it has an match action pipeline processing built in. So if you look at the Mellanox NVIDIA ConnectX 5 onwards, they do have some processing engine in hardware. If you go towards the more modern approaches to this, is you now have an ARM core on the NIC itself. So what's your how many ARM cores do you have on yours? 10 ARM cores and a lot of RAM available. That is what an IPU is. Whether you're Intel, you call it IPU, or NVIDIA, you call it, or Marvell calls it DPU. It's the same thing. Basically, you get this. You get a match action engine, which is an ASIC, not typically it's an ASIC. At least I know AMD and Intel, it's an ASIC, which is what we're targeting for PC, because it's a match action table semantic, right? So there are two modes. One is you can totally run everything on the host, where you turn off, you have no visibility into this ARM code at all. You're just running your stuff here. When I run TCP4 control add, basically goes and adds it here. So when the packet comes from outside, it's processed by that, heading to a VF or whatever, then ends up into this engine will redirect to the appropriate VF. So you could stick these VFs or SFs if you're the lesser performance variant. And I don't know what you guys call them. You call them SFs as well? Yeah. So you could stick them into a VM, you could stick them into a container, you could stick them into a container inside a VM. These things here. And so the first mode, which is the SmartNIC mode, is through, I believe through DevLink these days you can do it instead of a proprietary interface. You can tell it, I want to run into the SmartNIC mode. And at that point, you have no access to anything. This is abstracted out to you in the host. So you add your entries, they show up here. And what's interesting in this mode is these ports will also be abstracted for you on the host side. On the host, you'll see the ports, so you can control them as well. You can bring them down, up, but the wire is over here, right? The wire is on the NIC. That's mode one. Your PC, or if you write your own interfaces, controlling this, it's sitting on the host. There is another mode. For good reason, sometimes you don't want to trust the host. Again, it boils down to trust. I do not trust the host to be, someone could manipulate the host, and we're going to, we need to have total control from remote. There's an out of band port here, right? Which is not showing here. But all these NICs, here it is. All these NICs do have either a BMC or a hard-coded onto the hardware out of band port. That's just used for control. So if you have zero trust on the host, then this is what you do. You use the other mode, right? In that case, you have no visibility into the match action engine from the host. The host, it looks like a dumb NIC to you, right? And in fact, you don't even see the wired port sheet. You just see the SFs and the VMs. So we support both modes. You can turn off the SmartNIC mode, and when you you can turn off the visibility into the XPU, and your TC rules will just end up going somewhere here, right? When you run the TC control, it will go through the TC NDO on the driver on its way, and it's going to land there. On the other hand, if you run the XPU mode, your control plane is sitting on the ARM code. Such a case, of course, your driver here, which has access to IE, would be the one that's updating this. So any questions on the two modes? Your choice. You could do more offloads if you use your ARM code here. There are other accelerators, which I'm not going to talk about, like crypto. That has nothing to do with the match action engine, which is what our target is, or storage, etc. We really do not want to be programming that through, for example. So the two modes are mutually exclusive. So I think through DevLink, you either say, I want to run in this mode where I have no visibility in there, but the abstraction of this thing exists on the host. Or you can say, turn it on, and then everything I control, I run TC over here. The other thing we've been discussing, we've been doing a lot of discussions on how to map a whole PCI device into a TC block. At the moment, we're saying it'll have to be done manually by a human. So what they say is say TCQ disk add EN01 block 21, adding as many devices as you want. And we assume the switch dev model, right? That's what we assume. There is some concept of network versus host port in that this is a semantic that exists within P4. When you write your P4 program as such, you can say add a simple if statement here. Instead of saying apply, as you can see here, for example, I add an if statement which says if the header IPv4 is valid and its protocol is IP proto TCP, then I want you to look up this table. But I could likewise add and from net port, something like that. I'm simplifying. So they have this concept where they bit different from us saying, you know, if I'm going to be sending packets out, I'm going to attach this to egress. Or if I'm receiving packets in, it's going to be on ingress. In their case, you can attach to. It will look at the directionality. Are you going this way? Then you're going to the host. Are you going this way? Then you're going to the net. Before program will take care of it. Whatever this thing is, it knows how to handle it. And there's multiple ways of handling this. We have a scheme that we use. I talked about TC, SmartNIC versus that. The network ports in this. So I just want to distinguish them. These are network ports because they have a cable connected to them. On the other hand, these are VFs or SFs, the virtual ports. They exist. They call them host ports. So you can actually write a program that just deals with host ports. Yeah, I don't know who really came up with this naming convention in the P4 world. Occasionally, we run into one issue where there is only one port. Someone wanted to just receive on one port, take it, and wanted to watch the packets. So this port was neither host nor it was acting as both. You see, this would be pretty easy because you say ingress versus egress. And so we have an issue open right now. Never thought that a P4 program, someone will only want to write a program that deals with only one port. So they reported a bug to us. We didn't get it first. But after, running their programs, this guy's assuming that this one port he has, which he was doing some sort of, I think it was Rocky V2, is both ingress and egress and is a host and a network port. He doesn't want to use any of the other ports. So there's still some fault. What else can I? So again, if I was to go back again, the summary of this is we're following the TC model, right? That the TC model, and the summary is if I have a software data path, I have a hardware data path, or I can have one or both. These are the models. I could have a totally software path. I could have a totally entirely hardware data path. I could have a hybrid scheme which, because I don't have enough space in my hardware, so the software then becomes an exception path. Right? I want to do 500,000 and my hardware can only do 250,000 table entries, in which case I'll program what I want in hardware and then the rest can be processed by software, like in a slower path. I can have a piece of hardware that does not support specific actions. And again, this model already is supported by TC as is. This is already supported by TC. This is how TC Flower or U32 works today. This is already supported by TC, where a table for just this one specific action, hardware can't do it. So you have to continue, you have to execute this action in software. And the third model, which is a small change, which basically builds on this, on the action continuation, is the hardware continuation, where you have the first table in your pipeline is sitting in hardware. That's the only thing the hardware can do, and you want to offload that, but continue processing the rest in software. The other thing to emphasize as far as the TC model is concerned is we're assuming a single P4 program that will be shipped by the vendor that you can replace if you wish. you'll have to talk to them about support for that, but total freedom basically. In that this program will only be loaded on a reset. You're not gonna, even if your vendor, there is at least 1 or 2 vendors that can live replace the program. We're not dealing with any of that, right? At least not in the initial aspect of things. So you will, the driver will have to do a reset and then you load things. And then the question is, how do you deal with, I have a brand new program, I want to replace what's in there. Do we need to make changes to devlink, or do we need to have a symlink that says, this is where my program is, and I just change the symlink, and when I do a reset, it just loads the right one? Those are questions that still may end up coming to the mailing list when the drivers are working very well. We have some other small challenges that are still outstanding. The problem right now is the TC-NDO is still, well, I've shown that we made very little changes to the TC-NDO, but the TC-NDO is bound during QDisk setup, way before the filter. We may desire to have a single TC callback, a block that would use the ref count idea that I described earlier. TC callback mechanism doesn't understand the semantic, so we may have to make a change there. We're trying to make we're trying to avoid making changes, but there's a question of quirks like this that force us to. Do we need to, perhaps, when there's a reset, a hardware reset happens, do we need to up call into the stack, into the TC infra, so it knows that something needs replacement, right? For example, if you already have some entries in a model like this, even if you're reloading the same program with some small logic changes, in a model like this, do you go and flash all the table entries you've populated already? Or right now, there will be an event that user space will catch. Those are open questions. There's an old question that, if I want all the SFs within my PCI block to be automatically added to my P4 program, by today you will have, for example, in this model here, I don't know about your hardware. I don't remember how your hardware does, but you have to create the SF on the host, and then it pops up here. Am I correct, Anjali? Your hardware, right? The SFs are still being created. Sorry, the VF are being created using the sysfs on the host, right? So and the SF links are created from here. So the question is that
all of provision.
Oh, sorry, Mike for Anjali, because there are people remote who are listening.
Of all virtual ports happens from the embedded cores, only because SRV is bulk created on the PCI side, we have to do it on the host. But again, it's provisioning and configuration and everything. Representers, all of that are on the embedded cores, and SF, all of the functionality, provisioning and creation is from the embedded cores.
Okay, so yeah, there's that challenge. What happens if I want everything in my PCI block to be subjected to this P4 program? Should I just, it's just going to pop out? Should we automatically add it to the TC block? TC block doesn't support those semantics right now. So essentially, these are the discussions. So I summarized. This is a lot of text here, which I hope to publish as part of the conference documentation. But if you're interested, we have bi-weekly meetings. Sometimes we miss a meeting here and there, but there's a mailing list that is continuing to add in entries. And this is not the most up-to-date because there are other issues. Someone has to update this document. This is valid as of June 10th. Yeah, and I can open up to questions, commentary. Anybody?
Might be a bit of a stupid question, but for the hash that the driver has to validate, is that across the entire program, including all the software parts, or is it only the part that is installed in the hardware?
Both. So if we were, yeah. So you see the green things; those are generated by the compiler, right? So they have the same front end. All the you start with your P4 program. And that P4 program has to be the same one that the software as well as in hardware.
So if I add something to the P4 program that is not supported by hardware at all, and the compiler that is delivered by the hardware vendor actually generates exactly the same binary to be loaded into the NIC, but I have something extra in software, it's not going to work because the hash is different.
Yeah, in that case, it will object. However, I think the model you're talking about is a scenario like this, for example, right? Yeah. Where we have half, because the hardware can't do something. And we have, so I should have, sorry, I somehow my brain skipped this part. If you're familiar with TC, we have the skip software and skip hardware. That basically is essentially the scheme where you are, when you add entries to hardware, you say skip software. It's just targeted to hardware. And when you're adding to software, the skip hardware, right? That mechanism has worked. That mechanism is good enough for the exception paths, or when you have resource constraints, your hardware can't handle enough entries. So you as a human being with, based on your judgment call, you say this goes in hardware. In that case, there's no problem. This is the same program on both sides, same ID. So we extended that model. I should have raised that as one of the issues, the changes we have. Two tables. So you can say this table is hardware only, right? So we have this entry, this semantic which says skip hardware table. This table is only in software. You can't send this. You can't use this mechanism of you're sending netlink interfaces to the TCNDO for that table. This code somewhere in here will reject it. It's targeting hardware, right? And the hardware doesn't support that table. So that's the small extension. That's why I said in this case here, in this use case, this one, that currently not TC supported. But in any case, the IDs will be labeled and they will be checked first by the software infra and then eventually by the driver. If it's going to the driver will catch it if it's made changes.
So that answers the question about resource limitations of the hardware. What about functional limitations? Say we want to run this program in the hardware, but it can't because of some functionality the program's using, then what?
So the current TC model supports what we call action continuation. So this is what this use case is showing. It currently works, right? If you run an NVIDIA, or if you see me on my slides, I would occasionally say, I guess skip software plus pipeline continuation. PAO already supports this today, right? So what you do is you add. So look at this table here, for example, right? Sorry, this one. This one, let's say it's an exact match table or an LPM table. It supports two. When I wrote my P4 program, I said I want to support action A and B. However, this hardware is incapable of supporting.
Back up. I think you're missing my question.
Okay.
I write a P4 program. Something in that program itself, not a table. Something in that program itself. Is that always guaranteed to be able to compile into the hardware? What if the hardware itself can't run some piece of this program?
Okay.
Yeah, so I think Jamal explained. So you can annotate your program and say this does not go into the hardware because hardware cannot do it. And it is software specific. So it'll compile for the software backend. And that's what he was explaining. There is pipeline continuation.
So that's fine, but you do tell the user it can't run this program, right?
Yeah, I mean,
because obviously the last thing you want is to be surprised that what we thought we were running in hardware is actually in software. Now,
it's compilation time.
Okay. As long as the user understands all of that, that's fine.
put it back.
So that does not follow the existing TC model, right? Because the TC model is supposed to be you offload things opportunistically.
Yeah. So, and we're saying that we improved it. That's our claim, is that we can now tell, right, that it doesn't even hit the driver. We can, if it's been accepted, we can object to it.
So the hybrid path, Jamal.
Oh, it's Said.
Yeah. So do you have to cut in the middle, or like the middle part? If the part that the hardware doesn't support is in the middle, you can't inject back to the hardware.
No, you cannot. That you don't support.
Okay.
That we don't support today in TC. I think it's doable, but we don't want to go there. We just want to support the TC model. That's all we're starting with.
Right. Right. So my next question is, how do we support the exception path without, you had to change the stack, right? How do you know where to continue from?
So in the case of, this one is pretty straightforward, right? Because your hardware supports it already. Your driver supports this model that I'm describing here. Here it's already working. I mean, I don't know if Oz or Gal pressed. So I saw Gal.
I think they're an IPsec.
But basically, there is a concept of when you add an entry into the hardware, you specify a cookie.
Right.
So when your driver will up propagate.
This is what we call flow tag. So we use the same mechanism.
Yeah. So it's in this case, the action. There's a table. I think I have a feeling it sits in your driver in your case.
Yeah, it's there. So it's the same mechanism.
Yes.
Okay. And you can't inject back to them.
Well, if you're talking about saying I have, let's say this is the P4 program, right? I'm showing a P4 program and how things will work. If I have a third table and this one is in software, but the third is in hardware, that's what you're suggesting?
Yeah.
And that becomes that's not even supported in TC today.
Right.
You either have, today TC is either, the most common model in TC is a hybrid model, where the software data path is an exception or an extension.
Got it.
So you either don't have enough entries in hardware, and then you need a software data.
So is it up to the user to decide how to manage?
Exactly. Exactly. So
with the annotation thing you say?
The annotation is just to teach the compiler that this table is only for hardware, or this table has only 2048 entries in the compiler. When I showed the annotations here for the compiler, so in our case, we introduced our own annotation. You'll see everything's labeled as @score TC type. So you annotate throughout your P4 program. Unfortunately, you're assumed to already be knowledgeable about how you're going to deploy your program. So there's still some, I would love if this was totally fit for people who are not very knowledgeable, but you still have to know things.
Got it. So the compiler can decide on its own where to stop the offload, where to stop.
Yeah. Okay. So if you look at the generated JSON file, for example, which the PC uses to read, you'll see that it knows that this hardware has only 2048 entries. So if you try to send more than 2048, then this layer will stop you right here.
But this is just for the entries. How about the actions that are not supported, or if it close like?
So we have this concept. So just like we do skip software for entries, we also have skip software for hardware and action, for tables and action. That's something new we introduced.
Part of the annotation?
Yes, it will be an annotation that this is only available in hardware.
Got it.
So the interesting part here is we want to generate everything from the compiler. We do not want to change the kernel code at all, right? Of course, past the first patches we submit. We have to submit these patches, and once they're in, you can write your own P4 program. You can define your own protocol full. You do not upstream that. Of course, it would be nice if you make it available if it's useful. But it reduces the maintenance to the kernel from that perspective. And we're not inventing much new stuff. There is a little bit, unfortunately, NDO did not, I listed a few things during the talk, what TC NDO cannot support. right? The fact that TC block, for example, is a broadcasting. I send the fact that tables in TC are assumed to be pub-hot and we want them to be shared by a PCI device, for example.
Yep.
Simple things like that.
What kind of infrastructure you use to write the compiler? If I'm like a vendor want to implement it
So
backend?
there are two. We should talk to Martin from your side. He's working on a compiler backend. So there are two there's a compiler called P4C, which is open source.
Yep.
You can write your own backend. The input is a P4 program. In our case, for the software part, I shouldn't say we did it. We inherited some code. We extended it to generate BPF, that's TCL. Right? And so you can see if you're running at TC level, this API, if you're running software, this is only needed if you're running software, or you need an exception path or an extension to your pipeline. We invoke kfuncts. Not every P4 object can be abstracted easily or without a square hole feeding a very big round hole in eBPF. Like an extend cannot. Extends are extends. There is no concept of extends that matches.
Yeah.
Tables, yes, with some caveat, right? So we put all our objects here, and this is Netlink. Controlling it the same way as Flower. We have the TLVs. We get for free all the Netlink error checking and all that stuff. The hierarchies of IDs, which is important in Netlink. In P4, that every object has an ID. What happens that fits very well with the T part of the TLV. Right? And so if you have every object with that ID and the hardware knows what these IDs are, the software knows what these IDs are, and you can cryptographically validate that the same ID is for the same program, then it's a very natural fit.
Yeah, so this is the common design for the compiler, but more interested in learning about the backend where the hardware limitation or the vendor specific
so
implementation comes in.
Let me see if I have a diagram I can show. Maybe this one. Oh, sorry. What am I doing? Not a very good diagram, but I think it may be able to help. Right? So you have your P4 program, and you have a target architecture constraint, so you will be able to specify your hardware constraints.
Oh, it's constraints, like, I got it. Okay.
Now, there are some people who do a lot of clever things, like, because they're used to the best effort model, where you're shooting to the driver and hope the driver has a way to optimize and squeeze the last byte out of the TCAM. In our case, what we're doing is, I don't want to play any of those games. My program, the compiler knows I can put 1 million entries for your hardware.
To translate to TC, yeah.
Yes.
Yeah. Okay. Okay. Makes sense.
Okay. Can we put them on the screen or they? Okay. Well, yeah.
Hi there. Can you hear me? This is Chris. Hello.
So who is this? Identify yourself.
This is Chris Summers. Hi.
Hey, Chris.
Hey, buddy. I just wanted to kind of give a show of support for this project. I've been playing with it, with the current work in progress, the pure software mode at this time, and I find it to be extremely promising. It checks all the boxes for me in my use cases. I want to be able to go from pure software and then later add acceleration as a future option. But right now, even the pure software mode, I can use in a production deliverable. It actually has some very valuable features in it. And I just hope that we can get this upstreamed, soon and improve it over time and, not split hairs anymore. Let's get this thing going. It's really powerful. it brings P4 to every PC. P4 has been very elusive because it's been run kind of in custom environments. Every platform sort of had its unique attributes, and a lot of the SDKs were closed source, and you had to get licensing, spend a lot of money. This democratizes P4, ties it in with the eBPF, makes it available on every platform. I really can't say enough good about it. So I just wanted to say that, and I hope it moves forward. Thank you.
Thanks for your support, Chris, and virtual beer is coming your way. Not as a bribe, but as a thank you.
Okay.
So in your model, do you know how you would delegate access to a table to another entity?
Okay, so you're talking about, actually, we had a discussion. I don't know if it's here. You're saying, let's say I want to use FTP. I want to run FTP and invoke.
No, that's not the so can you scroll back to your SmartNIC thing or IPU thing?
This one here.
So let's say that you create you load your P4 program, but you want to give a VF an access to populate a table. How?
Like you want to give the root control to
just ability to add rules to a table, right? You create a pipeline, and let's say you want to give the VF the ability to add n-tuple filters. So today it would be an if to n-tuple filter, but obviously with this you can define your own fields in the headers, so that you can't just use n-tuple filters anymore, right? Because you need P4. So how does the VF know?
I see. So you basically want some hash to select a VF.
No, the VF itself wants to install its rules, right? You created your own protocol because it's P4, and you can create your own protocols. So now the Linux networking stack does not understand. You need P4 in the VF as well. How do you populate the tables from the VF if it only is the controller that knows what the parser graph is?
I guess I'm trying to understand the VF being able to install a rule. Is this, there's some other entity like if tool or something like that, right?
No.
Sorry, say. I'll repeat the question. Just say what the comment is.
Like today, when you have a VF, the VF can sometimes create its own rules, right? Like that's just something that certain NICs allow. The VFs can create rules and install them into the hardware.
At boot up time or
no, like using if to n-tuple filters. Google supports it in the cloud. Many companies do. If you want to do flow steering or some other kind of filtering inside the device, right? You can create an n-tuple filter using if to install it into the hardware, so that the packets don't come into the VM at all.
Right. This is a replacement for or an equivalent to what if tool would do?
I'm asking you what your replacement is if you're using P4 to define the parser and you have no ability to expose it to the VM. How does it know how to install rules?
I think I'm going to have to talk to you after, because I'm not sure I fully understand. But if if each tool is doing it, we should be able to do it using maybe some extensions or.
Would that extension look like what I suggested on the mailing list?
All right, let's talk after, buddy. I want to be able to support it. I just need to understand it better. Any more questions? Remote? We still have 7 minutes. There's one more question. Come.
I think he was simply saying that even dumb NICs aren't that dumb anymore, and you end up having to layer stuff on top of each other, and you can't just assume that the host NICs are stupid.
I think I don't want to blame AI for this, but there is a lot. Now, I'm not saying that AI needs a lot of these features, but there is some drive, and I probably want to blame the cloud vendors. Because cloud vendors invent their own protocols all the time, and they have good use cases for this. The idea that you invented, I don't want to say quick or something new, and you have to go through upstream or go through the ITF is probably not the most time-effective thing to do. This allows you to make changes of that sort. So statefulness is still a challenge. You can't just go and implement TCP or TCP stack on this. You can implement helpers for it. It knows how to do statefulness, not to the extent of being able to do expensive things like what TCP does. And there are vendors who are using it for that kind of, like, I don't want to mention any names. Yes. I do believe that we have to start considering there, even though it's my big concern is the big cloud vendors know how to do this, and everybody else is not enabled. And the other concern will be every vendor has their own SDK, and they're going outside of Linux. And I'm a Linux bigot, and I'm also pragmatic and say that the API should be Linux. I'm not going to point to any vendor, but not what the other vendors are trying to sell as the best thing. And that there's no other questions, then thank you for coming. We took the smaller room, so it worked out very well. Thank you.